This lesson is for section 10.7. Today we're going to be working with polar curves. So now that you had an introduction into the polar coordinate system and you've had some practice with graphing in the polar coordinate system, now we're going to take it a step further and we're going to actually graph polar equations. Alright, so let's begin first with graphing two very basic polar equations. We have r equals 5 and theta equals negative pi over 6. So really we're looking at r equaling a constant and theta equaling a constant as well. You might not be as comfortable calling that a constant because usually we plug in, theta values, but this is just a real number. Negative pi over 6 is a real number, so we are dealing with theta equaling a constant. Now graphing these polar equations is very similar to graphing the rectangular equations x equals a constant and y equals a constant. So let's say I wanted to graph the rectangular equation x equals 3. When I graph this, what I'm looking for is to graph all of the points for which x is equal to 3. So let's say I was trying to graph every single one here with a point. Well, clearly there's going to be an infinite number of points, so I indicate that by a vertical line. Obviously from Algebra 1, you already know how to graph x equals 3, but it's that concept here that we're going to apply now to r equals 5 and theta equals negative pi over 6. If we were to switch variables and want to graph y equals 6, it doesn't matter what x is, it's every single point for which y is equal to 6. So we graph, in that case, a horizontal line. Now, when you get to r equals 5, you don't care what theta is, you just want to know all of the points for which the distance to the pole is 5 units. So I'm going to mark off here 5, okay, and I want to know every point for which the distance is 5 to that pole. So that's going to form, if I were to draw out every single point, an infinite number again, but that's going to form a circle. And we talked about that already in the previous lesson. Whenever you try to graph r equals a constant, I think I called it a, you're always going to get the equation of a circle that's centered at the pole. Now when we graph the polar equation theta equals negative pi over 6, here we don't care about r. Here all we want to know is every single point for which you have an angle measure of negative pi over 6. So because this is negative, you have to remember that you're going from the polar axis in a clockwise direction, but you're looking at every single point in the polar coordinate system that has an angle measure of negative pi over 6. And again, because you don't care about the r value, remember that every point in the opposite direction, okay, would be defined as negative r comma negative pi over 6. So we include all of these points as well, which forms a straight line again. Okay, so that would be the graph of theta equals negative pi over 6. So just make sure you're comfortable graphing these two basic polar equations. So anytime you see r equaling a constant or theta equaling a constant, you'll know what to do. Alright, now in number 2 we have a function whose polar form looks a bit more complex than the last two graphs that we had. Here we don't see r equaling a constant or theta equaling a constant. Now we have the polar equation, r equals 6 times the sine of theta. Now when you graph a function in its polar form, what you want to do is find what values you have for r when you increase theta from 0 to 2 pi. So as you can probably tell from this obnoxiously large table here, you can, anytime you graph a polar equation, you can always use a table of values. So you would plug in theta from 0 to 2 pi and find the corresponding r value. So we're going to fill this table out. I'm just going to show you this particular graphing technique because it of course does work. But I also want to help you visualize what's happening as you graph any polar equation. So anytime you graph a function in its polar form, what you really want to know is what happens to r as theta increases, okay, from 0 to 2 pi. So actually writing it like this, r comma theta, almost implies that r is your independent variable, but really theta is what dictates what the r value is equal to. So it's kind of strange that we write it as that coordinate pair. Really, I think it should be theta comma r, but just by convention they write it as r comma theta because to me it makes more sense to have theta as your independent variable, but whatevs. Okay, so to help you visualize what's happening in any polar function, okay, I want you to think of a spinner from a game board. So as you rotate your spinner counterclockwise, that's going to represent theta as it increases from 0 to 2 pi. Okay. Now on this spinner, we also have increments, values of r that are indicated here. Here we have an r value of 1, 2, 3, 4, and so on. Those are my positive r values, and obviously that can go on infinitely. But we also have negative r values, so that indicates negative 1, negative 2, negative 3, negative 4, and so on. So let's say I plug into some function a theta value of pi over 4. Okay, and I get a corresponding r value of, let's do 3. So what this is saying is that at pi over 4 I have an r value of 3. So I would increase and rotate that spinner here till I get to pi over 4. And at pi over 4, I'm going to be contained on the circle radius 4. Okay, so it's somewhere plotted on that circle here, and then we end up with that coordinate. Okay, so again, we're just increasing through our polar coordinate system from 0 to 2 pi. Now I haven't addressed why it's only from 0 to 2 pi, so let me do that real quick. So let's say we graph this point 3 comma pi over 4. And then I graph, again, 3 comma pi over 4 plus 2 pi. Well, I end up with the exact same point. So anything outside of this particular interval here, from 0 to 2 pi, I'll get the same exact coordinate. So it's unnecessary for us to look at anything beyond 2 pi, from 0 to 2 pi. So imagine now that you have that spinner and you've got instead, let's say instead of plugging in, when you get pi over 4, you get -3, okay? Now we're still pointing at pi over 4, right? Our spinner's pointing at pi over 4, but our tail end now over here is going to have a radius of 3, so we'd be plotting this point over here. So that's the general idea. As you graph a polar function, you're going from 0 to 2 pi, and think of that spinner rotating and plotting points on that spinner. So we're just indicating an R value using our spinner as it rotates through. All right, so let's come back to our original function that we're trying to graph, r equals 6 times the sine of theta. Now, we can fill out this table to show what happens as theta increases from 0 to 2 pi. So I'm going to pause and actually fill out the table. All right, so there's our table of values, and I put some decimal approximations there, so it'll make the graphing of those points a little bit easier. But what we're going to do is imagine that we have our spinner resting at that polar axis, and it's indicating right now that we are at 0 radians. Now at 0 radians, we have an R value of 0. So we're going to graph, basically, we're at the pole, right? Now, as we rotate this spinner and we increase theta, right, to pi over 6, now that spinner is going to be pointing at pi over 6. So here's our tail end down here. Now what we're doing is plotting the R values. So R rests on that measure, so it actually changes the length of the spinner, okay? It changes the length of that spinner to 3, so it's increasing the length of your spinner to 3, and we're going to indicate that with a point here. Now I continue to move that spinner, okay, to pi over 4, another known value here, and I get an approximate value of 4.2. So now my R value, when that spinner here is pointing at pi over 4, is going to move to a radius of 4.2. Okay, so right outside that circle. Okay, now I'm just going to pause the video and plot the rest of these points from 0 to pi only. Okay. All right, now what I think are the difficult ones for you guys to graph are points like these negative R values, but also when you get to something like pi over 2, 6, because right now your spinner, okay, tail end is down here, it's pointing at pi over 6, or pi over 2, I'm sorry, and it has an R value of 6, so that's why that point is graphed right here, R equals 6. The other one that I think is tough, so anything really at the axes are difficult, but pi 0, so right now it's pointing, that spinner is pointing at pi, okay? We have an R value of 0, so we're right back here, okay? Now, when we swing and we get into 7 pi over 6, so when that spinner starts pointing here, oh, that's terrible, that wasn't even the right line. Okay, so I'm here. Now we have negative R values, right? So I'm supposed to have a negative R value. Well, my negative R values are on the tail end over here. So when I want to graph 7 pi over 6 negative 3, that's actually right here, okay? When I want to graph 5 pi over 4 negative 3 root 2, now my spinner has moved. It's continuing to move counterclockwise here. Now my tail end is down here. Let me erase, there's a lot going on right now. So tail end is here, okay, and I have an R value of negative 3 root 2, so outside of the circle radius 4, here's where that negative R value is going to be indicated. So I'm actually plotting right on top of the points that I've already graphed from 0 to pi, okay? So here we have a circle. Oh, I haven't explained why we're going to connect it like that. All right, now we are just graphing very distinct points here in the polar coordinate plane. Now, if we were to find even smaller increments, so if we were to find, you know, values like pi over 12 or even smaller and smaller and smaller between 0 and pi over 6, we're going to see that these points plot like, that was pretty bad, they plot in a smooth curve, okay, to connect these 2 points. We don't just connect them with a straight line, okay, that's absolutely wrong, because those points, as theta is increasing, okay, R is increasing, so I can demonstrate this physically with you guys tomorrow if you're confused at all on why I'm graphing it with a smooth curve here. But for right now, just take my word for it that we're going to graph these with smooth curves, and we end up forming a circle. Okay, so this circle here has a radius of 3, and it's centered at 0, 3. Okay, if you were to convert this rectangular equation, or sorry, polar equation into its rectangular form, you're going to actually see that you'll have a circle with center of 0, 3 and a radius of 3. Okay. All right, now after you've seen how the table of values corresponds to the points on that particular circle here, I want to show you an even faster method for graphing a polar equation. So as you can see, graphing a polar equation can certainly be done using a table of values, right? It's just very inefficient. It took us forever. I'm certain I don't have to convince you that you'll never want to do that way again, because it just takes so long. You have to evaluate cosine and sine functions, and it's a long process, right, to find all those points. So instead, I'm going to show you another method where you rely on graphing this function as if it were a rectangular function. Then that gives you a guide, a reference for graphing the polar function. Okay, so instead of having an xy axis, we're going to use a theta r axis. So we've got theta here instead of the x-axis and r instead of the y-axis. So I graph this cosine function like I normally would. I have a general shape that looks like this. Okay, and what's nice is that this already shows me what happens as theta increases from 0 to 2 pi. Okay, we are experts at graphing this, so I don't think I need to explain this very much. The amplitude is 2, okay, but I'm shifting it up 2, so that value becomes 0. This is now 2, and this is 4. All right, now the reason why we're graphing this as if it were a rectangular function, I just want to be clear, this is not a rectangular function, right? But the reason why we graph it as if it were a rectangular function is so that we can actually see visually what happens to r as theta increases from 0 to 2 pi. So this is basically acting as a table for us because it's showing us a table of values. It shows us where our function is increasing and where it's decreasing, okay? All right, so now let's graph this polar function, right, in its actual correct polar form, okay? So we'll use that rectangular form of the function as a reference for when we try to graph it in its polar form. Okay, so we want our spinner to start at theta equals 0. So it's pointing at theta equals 0. I don't want to keep drawing the tail end here, but that's your tail end, right? Now from our graph, we can clearly see that when theta is 0, we have an r value of 4, that coordinate right here. So when our spinner points at 0 radians here, we're going to mark a radius of 4. So that's our first coordinate here, this point 4, 0. Okay, 0 in radians, not the point 4, 0 like the coordinate system, although it is similar, right? Okay, now as theta increases, so as we move our spinner counterclockwise, okay, our function, as you can see here, is clearly decreasing. That r value decreases, and it's decreasing until it gets to pi over 2, where it becomes the value 2. So as our spinner spins around and it faces, so it's pointing now at pi over 2. So here's our tail end. At pi over 2, now our r value is 2. So I'm going to graph the point 2 comma pi over 2. So this part, I'm going to try to color code this. This part of our function is decreasing here. Okay, and I'm going to indicate that. So here I've got when our spinner is pointing at 0 radians, here I'm at this point 4, okay, comma 0 radians, and I graph this with a smooth curve, but it's because it's pulling it in to the radius here of 2. Okay, so let's do that again. As I rotate the spinner, it's so hard to show you guys this visually on my computer, but as I rotate that spinner around to get to pi over 2, it sucks in and decreases that r value till I get to 2. Okay. Now my spinner is, so let me erase the first spinner here. It's going to erase probably the axis as well. Sorry. Okay, so now my spinner is at pi over 2, right? Well, as I continue to rotate that through, that's going to represent this portion of the function. So from pi over 2 to now pi. So that spinner keeps rotating. Now it's facing pi. All right, so there's the tail end. Now I have the point 0 comma pi, 0 radians, pi. Well, 0 radians is right here. So this is really strange, and I think this is the hard part for you guys to graph. You have to think of this as a radius that is being shrunk, right, till we get to 0. So we're at pi over 2. As we increase theta values, see how that radius is shrinking until it gets sucked in here right to 0. Now, once we go from pi to 3 pi over 2, so we continue to swing this, I guess it's purple now, but we swing this spinner this direction, still counterclockwise. Let's try a different color here. Let's go green. All right, now my spinner is going to be facing 3 pi over 2. Here's the tail end now. At 3 pi over 2, I am back at, it's increasing, right? Our function is now increasing. I have a radius now of 2. So I'm going to indicate that with 2, comma 3 pi over 2. That's that point here. So remember, this is an increasing function. So my r value, as this angle, okay, increases, the r value increases. So it went from 0 to 2. Now lastly, from 3 pi over 2 to 2 pi. So right now my green spinner is here. I'm going to still rotate it counterclockwise here until we get to 2 pi. And as that is increasing, as theta continues to increase, my r value is also increasing here. Okay, so it's increasing from 2 all the way to 4. So once it points, once that spinner now, okay, is pointing at 2 pi, now I plot the point 4 comma 2 pi, right? That's this coordinate here, okay? So I connect this coordinate with a smooth curve, and I'm finished with this function, okay? Again, we are only going from 0 to 2 pi. Now this shape is called a cardioid because it looks like a heart. How cute. So for Valentine's Day, you should give your significant other a cardioid. Sorry, I don't know what that noise was. I think that might have been a laugh. But anyhow, so that's our first function that we've done now with a graph as a reference. So we're going to continue to use that method here when we graph other very common polar curves. All right, in number 4, I went ahead and I graphed this function as a rectangular function, okay? So it's a quasi-rectangular function. Here's r, here's theta. Now this one is going to be a lot trickier than the last one that we graphed because here I actually have negative r values. So remember, when you graph a negative r value, you have to go in the opposite direction of theta, okay? And that's really confusing for students, so I'm going to go through this a little slower, and then hopefully I can pick up the speed when we graph the next couple questions. Now another thing that makes this graph a lot trickier than the last problem was that whenever you graph a function, it's always really important to find the zeros of the function, and it's no different here when we graph in polar form. We want to find the zeros of this function. So I actually have to find where my function 2 cosine theta plus 1 has an r value of 0. So that's going to be at 2 different values, right? Really what I'm doing is I'm solving this equation 0 is equal to 2 times the cosine of theta plus 1. In the last problem, we never had to do that because the graph just so happened to hit a 0 at the very bottom of the graph. So we already had the 0 of the function. Here, we need to find it. So we're going to solve negative 1/2 is equal to the cosine of theta. So we have 2 values for theta. Theta can equal 2 pi over 3, or it can also equal 4 pi over 3. Okay. Now, that's significant for us because when we try to graph this in its polar form, that tells us when we're back at the pole, right? That has an r value of 0. All right, so let's start with our spinner pointing at 0 radians. At 0 radians, we have an r value of 3. Okay, so I plot my first point here. Now, the function is clearly decreasing again, so in this cosine function, it's no different than the last one. It's decreasing till we get to pi over 2, where our r value is now 1. Okay, so as that spinner rotates, this measure is going to decrease till we get to 1. All right, now here is where it's really important to make sure that you find the zeros of the function, because from pi over 2 to 2 pi, remember this is 2 pi over 3, our function is still decreasing, but it goes from 1 to 0. So from here to about 2 pi over 3. So let's mark that here, 2 pi over 3. Okay, that's kind of close to 2 pi over 3. This value, as it increases as your spinner, okay, keeps rotating in this direction. Okay, oh shoot, bring that back. There we go. Okay, so as it continues to rotate, now it's kind of acting like like an asymptote. You can think of that pi over or 2 pi over 3 here. That's that measure. So as that spinner is pointing in this direction, here's the tail end. We're back at the pole. We're right here. So as we increase, we can't pass that pi over 6. we come right into here. So let me erase everything else so you can just see that curve. So that's the curve from this portion, that green portion on the graph. All right, now here's where it gets even trickier, okay? When you go from 2 pi over 3 to pi, these values have a negative r value. So this is where it's really important to understand this whole spinner concept. So we're here, right? This is where our spinner is now. As we rotate, okay, till we get to pi, now we have negative r values. So our spinner is still pointing in this direction, okay? And as we get to pi, the tail end over here is pointing in the opposite direction. Remember, negative values have to be graphed on this side of your spinner, okay? They're in the opposite direction of the angle. So when we want to graph this point, pi, or sorry, the theta value is pi, but -1 pi, we want to indicate that on the other side, so here's pi, we want to indicate that on the tail end side of your spinner. So we're over here. All right, so I think it's easy to see why the point is at, you know, -1 pi is graphed here, but how do we draw the function between those values? Because right now we could do that or we could do that. So this is really important, okay? This is important that you understand why this is going to happen. Now, we're trying to graph stuff between 2 pi over 3 and pi, right? So right now, this spinner is pointing here, this direction. The tail end is on the opposite side over here, okay? So basically, right now, everything that would be pointing here is now being reflected. So here's the measure 2 pi over 3, right? Everything inside here that we would normally graph here has a negative r value. So that means we have to reflect it over to this side where your tail end is, okay? So that means that this portion of the graph, which I'll do in this little light blue here, this portion of your graph needs to come over here. This is the reflected side, okay, using pi, 2 pi, or 2 pi over 3 to pi, using this here as your boundary between, you know, on the other side, you've got the line 2 pi over 3 and the line pi here, the opposite side. Okay, I hope I haven't completely blown up your brains at this point, but I'm going to erase now, and then I'm going to pick back up graphing from pi to 2 pi, okay? All right, so now I'm going to switch colors again, all right? And I just try to clean up the graph a little bit without erasing what we'd already graphed. And now I want to go from pi to the other 0 of this function. It's important always to try to go back to your zeros. You have to always indicate zeros. So from pi to 4 pi over 3. So our spinner right now, let's say we're starting at pi, tail end over here. I want to go rotate it until we get to 4 pi over 3. Now, 4 pi over 3 is pointing in this direction. So here's my tail end, okay? Now, everything that's graphed in between pi and 4 pi over 3 has a negative r value. So that means everything is going to be reflected on the other side of this graph. So those values here are now going to appear inside here. Okay, so at -1 pi, we're still here, but as we rotate towards 4 pi over 3, now that point becomes 0 pi over, or sorry, 0 4 pi over 3, right? This coordinate here is 0 4 pi over 3. So we're sucked back to the pole. So we're here, and as we rotate this direction, we're reflecting it to the other side. It's sucking back to the pole. All right, so that right now is our graph with those colored portions. Again, I try to erase so that it keeps it clean. Go back and rewatch a certain part if that doesn't make sense yet, because it's really important that you understand how we graph those R values when they're negative. Okay, now it's hard to switch colors again. Let's do red one more time, I guess. Let's do red for here. All right, these are going to be a lot easier now that we are switching back to R values that are positive. Okay, so again, we are right now, we're facing towards 4 pi over 3. So this is where my spinner was last at, 4 pi over 3. Now from 4 pi over 3 to 3 pi over 2, so as it continues to rotate till it gets to pi over 2, we have positive values, so that's great because everything's going to be graphed on this side now. So it's no different than what we were doing, originally. So we've got a value of 1 at 3 pi over 2. So a value of 1 here at 3 pi over 2. So now I have this curve. I said I was going to do it in red, I think, right? So from here, where it's currently at, right, because it was at 0, 4 pi over 3. So we're at the pole again. Now we go out till we have a radius of 1. And let's do this last larger portion here with blue one more time, I guess. Or did I use purple? Oh, I haven't used purple. I'll use purple. Okay. Now from 3 pi over 2 to 2 pi, this is going to be a lot easier, just like that first curve was too, this very large portion of the curve. So from 3 pi over 2, so now we're pointing here, okay? That's where our spinner last was. We're at 1, okay? And we're going to increase the radius to 3. This is the R value, 3. So we're increasing as we spin this towards pi to 2 pi. So we're at 3 pi over 2. We spin it towards 2 pi. This is increasing until we get to an R value of 3. All right, so let's clear this up. This is, yeah, it's kind of bad. This is called a limacon. Limacon. Oh, I think I have it in words here. And I think it's a French word. It's got a little like italic thing. I don't even know what those are called when you see that C. I'm so uncultured. But this is a another very common polar curve that you're going to see, and it's got that inner loop, okay? Okay, now from here on out, I'm going to try to go a little bit quicker when we graph through these, because I know this is getting long already, but if you're not following why the curve looks the way it does, you need to really focus on problem starting with number 3, and then definitely number 4 here, why we found the zeros, and what happens when you have those negative R values, okay? So 5 and 6 are going to go a little bit quicker. Okay, now when we consider the graph of 3 sine 2 theta, normally what we would do is we would set 2 theta in between 0 and 2 pi, and then we would have you solve so you find 1 full period. Okay, so we end up with a full period of pi. But remember, when you graph in polar form, you always want to know what happens to theta as it increases from 0 to 2 pi. It's got to go all the way around. So here, we actually get 2 full periods in our graph. So we're going to graph this here. Here's one sine function, and then that second period here. So this now is 2 pi. Here we have a value of pi, and then your intervals would be the same as if you were to graph just within here, but that's going to be your graph, so I'm going to pause and finish it off. All right, so here's our graph, and again, we don't have to solve any equation because clearly we can see the zeros of our function. Now, let's start with our first point. When the spinner is pointing at 0 radians, we are at a radius of 0, so we're at the pole, and as we increase to pi over 4, so let's point our spinner in pi over 4, okay? Now we increase to 3, so we are on this circle with a radius of 3, right? So that point is about right here. So as we increase in this particular section of our quadrant 1 here, this is going to increase till we get to this value. Now, as we get to, or once we get to pi over 4, now it starts decreasing again. Okay, so we're getting sucked back to the pole when we get to pi over 2. So as we graph this direction, once we get to pi over 2, we're sucked back in. So we start decreasing until we get to 0 once we get to pi over 2, okay? All right, now, here's where it gets a little bit trickier again. Let's do this portion in purple. So from pi over 2 to 3 pi over 4. So now this time, your spinner's pointing that direction, and we're going to go to 3 pi over 4. So within here, now I have negative R values, so everything's going to be graphed on the opposite side. So they're going to be graphed over here. Everything's going to be within here. So now I'm going from a radius of 0 and increasing it to a radius of 3. So it looks like this. Okay, as I move up this curve from 3 pi over 4 to pi, I'm still, even though it's increasing, guys, it's got negative R values. Okay, so we're here, right? We're within this, but we've got negative R values, so it's really graphed on the other side. So there's the other loop here. Okay, now let's do this next portion in green. All right, now we are at pi. So our radius, our spinner, I mean, is facing out here. We have a radius of 0, so we're still here. And we increase till we get to 3 once we get to 5 pi over 4. So here's 5 pi over 4. And we have a radius of 3, so we're right there, okay? So we increase like this till we get out to here, and then from 5 pi over 4 to 3 pi over 2, so from here to here, right, we still have positive R values, but they're decreasing, so they go from radius of 3 all the way back to our pole, so we'll connect that like so, okay? Finally, we have our last portion of the graph. I'll do this one in orange. From 3 pi over 2, so we're facing here. Now we're back to negative R values. So everything from 3 pi over 2 to 7 pi over 4, which is going to be facing here, everything in this portion of the graph is actually in its opposite direction. So that's going to be reflected over here, okay? So we are at 3 pi over 2, 0. Or 0, 3 pi over 2. Sorry, I keep confusing the two coordinates. Okay, so we're here at the pole, and it's going to increase to a radius measure of 3, okay? So again, you're in the opposite directions, but now that point is over here since it's reflected. So we go, remember we were graphing in here, so it's going to be drawn in like this, okay? And finally, to finish that off, from 7 pi over 4 to 2 pi. So in this portion, where you normally would graph, we reflect it over here, all right? And that's why as it decreases from 3 to 0, you're seeing it look like that. This is called a rose. Okay, to try to shorten up this lesson a little bit, I want you guys to try number 6 on your own. This is going to give you another rose. This time it's only going to have 3 petals, and make sure that when you graph this, the reason why I already drew this out is I want to show you that this is going to have 3 full periods, okay, that you'll see when you graph from 0 to 2 pi because of this cosine 3 theta. So you always have to be really careful about that, okay? So go ahead and try that one on your own and check with the key. All right, I was going to do number 7 in the video, but I realized that this is already a super long lesson. So rather than doing this here with you, because this is a really important question because the R value is now R squared. So I'm going to do this either in part 2 or in class. So just remind me tomorrow so that I make sure I talk about the lemniscate. Because this stuff is really hard. I know it's a lot to take in. You have to be able to graph, solve, and evaluate sine and cosine functions, and then on top of that, you have to do what we did in the previous lesson with plotting polar coordinates to even understand, you know, where to start in these problems. So is definitely the hardest thing I think that we've done the entire year. So please make sure that you watch parts again if something's still unclear, and definitely try to do number 6, because if you can be successful at number 6, I think you have a really good handle on this material. But thanks so much for sticking in there. I will see you guys in class tomorrow, okay?